7.3, triangle similarity with angle, angle, side, 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 and side, angle, side shortcuts for similarity. The learning target or objective for this lesson is for you to be able to prove certain triangles are similar using angle, angle, side, 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 or side, angle, side similarity. And to be able to use triangle similarity to solve problems. In the previous lesson, 7.2, we could only conclude that triangles were similar if we were told, or if you remember, for similarity, we had to have all angles congruent and all side ratios, or all sides, had to be proportional, which meant that their ratios had to be equal. And if we had that information, then we knew the triangles were similar. Well, Euclid came upon three cases where we wouldn't have to show all of that to know the triangles were similar. One of them is called angle-angle similarity. And I can draw some pictures in class to show you why this works later. But basically, if you have two sets of angles locked in, then the third angle in the triangle, since the angles add to 180, sets of angles is also going to be congruent. We already saw that in some of 7.2 problems. But those angles are also going to lock the sides and force those to be proportional. So we have what's called angle-angle similarity. That's actually a postulate. Then we have side-side-side similarity. That's a theorem, and side-angle-side similarity, which is another theorem. We're not going to prove them. We're going to use them in proofs. So angle-angle similarity says that if two sets of corresponding angles in two triangles, two triangles, are congruent, then the triangles are similar. That's the notation for similar. Notice congruent is the notation that has the equals and the tilde. Similar drops the equals, saying that the lengths are not equal, but the shapes are similar. The measures of the angles are equal, but the lengths themselves are not necessarily equal. So what this means is if I have a triangle, and this happens all the times in proofs, these are where some of those angles that we proved way back in the second unit of geometry come into play. One of them is the right angle congruence theorem. So this triangle, we'll call it triangle ABC, and this one DEF. Triangle ABC will be similar to triangle DEF by angle-angle similarity. It has the right angles congruent by right angle congruence theorem, which we proved, and a set of marked congruent angles. So that's enough for us to say the triangles are similar. With this postulate, which we don't really need to memorize it as postulate, we just need to memorize it as angle-angle similarity. With this, we can assume the triangles are similar as long as we know two sets of angles between them are congruent. So I say explain why the triangles are similar and write a similarity statement. If I use the triangle sum theorem, 180 minus 90 is 90, minus 47 is 43 here. So I have angle A and angle D are congruent because they're both 43 degrees. And there's my reason. I'm not going to write a definition or anything because it's just that they have the same number measure. I also have that angle B is congruent to angle E by right angle congruence theorem, which is a theorem in your flipper from their second unit of geometry. So that's kind of like our checklist. If you can show two sets of angles between them, and you can check off those two sets of angles, then you can say the two triangles are similar. So in this case, triangle ABC is similar to, notice I went from 43 to the right angle, so I got to go from 43 to the right angle. Similar to triangle DEF by angle-angle similarity. So here's our reason why the triangles are similar, angle-angle similarity, and here's the evidence. I have this set of angles and this set of angles congruent. These proofs are probably the easiest proofs we'll do this year, as long as you know what criteria you're looking for, angle, angle, and you actually go through and find it in the picture. In the next picture, I've had a lot of people say, well, Mr. Ritter, there's nothing marked other than the right angles. Well, then you at least know that A is congruent to angle D, by, in this case, the right angle congruence theorem. I sometimes just abbreviate it right angle theorem. But we again proved that back in geometry unit 2. So we have that set of angles. To use angle-angle similarity, we need a second set of angles. You need to look very carefully at the picture. There is a second set of angles, the vertical angles. So I actually can say that angle BAC is congruent to, so I did fat, skinny right, I'm going to do fat, skinny right, ECD, angle ECD, or DCE, it doesn't really matter for the vertical angles theorem. So now I've got my checklist. My criterion for using angle-angle is that I have two sets of angles congruent, which we have, and we have justified why they are. So now we can say triangle BAC, I did fat, right, skinny, is similar to triangle fat, right, skinny would be EDC by angle-angle similarity. So here's how the proofs work. Even when we do some application problems, as you'll see in a minute, we may have to justify some things using one of the three shortcuts to saying triangles are similar. Angle-angle similarity, which we just used, side-side-side similarity, which is up next, and then side-angle-side similarity. Side-side-side similarity says that if the three sides are proportional, it will lock the angles to be congruent, or at least that's what Euclid was able to show through a proof. So if three sets of corresponding sides on two triangles are not congruent, but are proportional, meaning they have the same ratio, then the triangles are similar. So you can think about it even like this. I'll give you an equilateral. Yes, I know equilateral has 60 degrees. We're going to pretend that we don't know that about the triangles yet. Let's say this is 4, this is 4, this is 4, this is 2, this is 2, this is 2. Well, we already know there's a scale factor to go from here to here of 1/2, or from here to here of 2. And those sides actually lock those angles all in to be 60 degrees on both triangles. But all I'd have to do is show that the ratio of this side to this, and this to this, and this to this, were the same value. And if that's the case, this doesn't even require justifications other than your ratios. If I can show that, then I can use side-side-side similarity to justify why the triangles are similar. Our last reason, there's a lot more when we get to congruent triangles, but for these we have angle-angle similarity as a shortcut, side-side-side similarity as a shortcut, and side-angle-side similarity as a shortcut. So with this, it says if two sets of corresponding angles are congruent, and this again is between two triangles, if two sets of corresponding angles are congruent between two triangles and the connected sides to that angle are proportional, then the triangles are similar. Not congruent, similar. Then the triangles are similar. So here's an example of what I mean by that. I have a triangle. Hey, look, it's a right angle. Darn, we didn't get any other angles. I have another triangle. Hey, look, it's a right angle. Darn, I didn't get any other angles. I can't use the easiest one, angle-angle similarity. But I can still say this angle and this angle are congruent by right angle congruence theorem. Now, if I have that this is 4 and this is 2, and this is 6 and this is 3, then I can show that this short leg to this short leg, the ratio is 2. This short leg to this short leg, the ratio is 2, or actually 1/2, because this to this would be 1/2. But anyhow, if I can show the ratios are the same, then I can say that this triangle and this triangle are similar by side, angle, side. Notice it has to be the two sides that are connected to the angle for it to be side, angle, side. Side, angle, side. For example 2, verifying triangle similarity. Determine whether the triangles are similar. If so, explain why and write a similarity statement. By the way, it depends for your similarity statement whether you're starting with the shape on the left or the right. You might get a different order, but it'll also matter based on your scale factor. If you remember back to lesson 7.2, the scale factor, triangle blah, similar to triangle blah, the first one, surprisingly, is our image, and the second one is our pre-image. So when we do our scale factor, if we've written a similarity statement, the one we put in the numerator should be the values that lined up with this triangle statement. The one that we put in the denominator, the pre-image, should be the values or the sides that line up with the pre-image triangle in our similarity statement. So here, I don't have any angles given, but I do have sides given. So I'm going to show, hey, look, PR looks like that matches up to SU, 2/3. Then I'm going to see that's one side, okay? Now I'm going to see if TU matches up to STU, PQR, if it matches up to QR. QR. Oh, wait a second, I did this in the reverse order. I put this one on top. So I have to put QR on top and TU on bottom because I started with this triangle on the top. So QR over TU would be 3 over 4.5, which divided gives us 0.6 repeated, which is the equivalent of 2/3. So far this checks out to be similar. Do the same thing for here, PQ. PQ over ST, which again is 3 over 4.5, which is equal to 2/3. Since the ratios are the same, since they all three check out to be the same number, they are proportional. Therefore, triangle, I'm going to do PQR. Wait, that's the one I put on top, right? Good, so that's my image. Is similar to its pre-image, STU. I just want to make sure that PR and SU match up, especially PR, SU, first, last, because those are the sides that are different. These are isosceles triangles, so I could change S and U, and here it would still be true. So here's my similarity statement. I just want to verify that this, my image, is the number I had on top, or that I could obtain this triangle by multiplying this one by the scale factor of 2/3. PQR is obtained by doing 2/3 times STU. Looking at letter B, they did give us an angle, which is really helpful because I've got the 70 degrees, so I have angle D is congruent to angle H. Because they're both 70 degrees, there's no theorem or postulate for that. It's not like it's vertical angles or congruent right angles or some other type of angle pair that we know. Now, the sides connected to this are DE, which is the short leg of this, so it would have to match to the short leg of that, JH. So I'm going to check out the ratio of DE to JH. And I wrote that wrong, to JH, which would be 2:1. And then I'm going to check out the ratio of their hypotenusi. This hypotenuse, DF, over this hypotenuse, HK. And I can't apparently write what I say this evening. So DF to HK, which is 5.8 over 2.9, which again reduces to 2/1. So now I have two ratios the same, and those are the ratios that touch the congruent angles. And so these triangles, DEF, notice I did fat, right angle, skinny angle, so I have to do fat, right angle, skinny angle. It might not be a right angle, it looks like a right angle to me, is similar to triangle HJK. Notice that D matches to H, E matches to J, F matches to K, by side angle side similarity. And so if I'm going to use this, I have to have those two ratios of sides that are connected to the congruent angle and have that statement also. So there's my evidence that supports why these triangles are similar. The scale factor again was 2:1, so I have to make sure the one that was in the numerator comes from the triangle that is stated first in my similarity statement. Had I started with the 1 or the 2.9 in the numerator, then this similarity statement would be reversed. For the last example, example C, for example 2, they don't give you three sides. since I don't have three sides, I cannot use side, side, side because I got to be able to show three ratios from sides that were given. So that means that I'm either doing angle, angle, or side, angle, side. They didn't give you any angles either. So you're probably not doing angle, angle. But if I look very carefully at the picture, I can always identify and use vertical angles. And so those vertical angles, angle TXU, is congruent to angle VXW by vertical angle theorem. So I got the set of angles, and then look, I've got sides touching this one and sides touching this one. This is the shorter of the two sides on the TX, so that's 12. The shorter on this one is 16, and that's XV. Those are both divisible by 3, reducing to, or by 4, reducing to 3/4. There's one ratio. I need a second ratio if I'm going to use side, angle, side, and it has to be the other side that's connected to this angle. So UX over XW, the longer of these two and the longer of these two, will match up, equals 15 over 20. Now if these ratios aren't the same, the triangles aren't similar. But in fact they are, because when I divide both of these by 5, I once again get 3/4. So I've now shown that the two sides connected to the congruent corresponding angles between these two triangles are in fact proportional. So notice I put TX in the numerator, so that has to be my image, my first shape. TXU, notice I did fat angle to vertical angle to skinny angle, is similar to, I'm going to have to do the same thing, fat angle to vertical angle to skinny angle, VXW, by side, angle, side similarity. These are some examples of how to use angle, angle, and side, angle, side similarity to justify why triangles are similar. In example 3, we're supposed to identify the similar triangles and write a similarity statement, but an important part that you're going to be assessed on is, can you also explain why they're similar using a postulate or theorem, and then calculate the measure. Now, a lot of times people look at this problem and they say, oh, I see side, angle, side if I look just at that right triangle. Cool, I'm going to use side, angle, side. And then they get to the bigger triangle and they say, look, I've got side, the whole side is 12, angle, uh-oh, we have a problem. I don't have the value of this. So I can't show a ratio for those short legs of the larger triangle and the smaller triangle without an actual number. So side, angle, side is out as a reason. So is side, 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 because I don't have three sides on both triangles. The only thing left to say why the triangles might be similar is angle, angle. Well, obviously angle EAB, or EBA, sorry, is congruent to angle DCA by right angles theorem, or by right angle congruence theorem. So there's one set of angles, but I need a second set of angles. Well, if you look really carefully, these shapes share an angle. The small triangle has angle A as one of its angles, and the large triangle also has angle A as one of its angles. Well, so that means that there is a second one congruent. I just don't see it as separate angles in the two triangles because they're a common or shared angle. This is also in your flipper, but we haven't really used it yet. A common or shared angle can be said to be congruent to itself. If something's on this side and this side, it's congruent to itself by the reflexive property of equality, or actually of congruency. So this works for these types of proofs, similarity proofs, and we'll also have a reflexive property of congruency when we're doing congruency proofs between two triangles. It'll be a little different though. Since they share an angle, angle A, we can say our second angle is that angle A in the one triangle, the small triangle, is congruent to angle A in the big triangle because they're the same darn angle. But the reason we put for this statement is reflexive property of congruency, POC. Reflexive POC. So we now have a similarity statement we can write. Triangle ABE, notice I did skinny, right, fat, is similar to triangle ACD, skinny, right, fat, by angle-angle similarity. Well, that's great, Mr. Ritter. We just did the same thing we did on the other page. How is that different? It's not. In terms of explaining why the triangles are similar, it's not. We have a reason and we have our evidence and we have to provide both. This is where they get you on quizzes and tests because you're like, oh, I'm supposed to find x. Okay, la la la, do all my problem, get my answer, great, I'm done. But people miss this direction where they're supposed to explain why the triangles are similar. So make sure that you read carefully, that you're going to say why the triangles are similar, providing a similarity statement, and evidence for your reason. Now, I have to find x. I'm going to do a proportion just like I did with dilations or similar shapes in 7-2. X matches up to 5. So I'm going to do big triangle over small triangle, B over S, big over small. So x over 5, this is the short side over short side. And then the long side AC is not 9 and not 3, but rather 9 plus 3, so 12. And the short, don't go with the short piece, the long leg on the baby triangle is from A to B, so that's 9. Now sometimes I'll have students actually write the letters out, but I think you guys will be able to do it without writing the letters to get the correct numbers. So this gives us 9x equals 5 times 12, which is 60. 60 divided by 9 is 6.6 repeated, or 6 2/3, which as an improper fraction is 20/3. So we found the value of x, and they asked, find the measure of each. In this case, the measure they wanted us to find was CD, and we lucked out because x is the length of CD. So for this one, CD is 6 2/3, whatever that unit is. Letter B. Letter B says find RT. Well, you have the option of calling STX or the whole thing of RTX. You get to pick. I'm going to call the little piece ST. I'll call that X. First, we have to explain why the triangles are similar. Well, they gave us one. Again, you see this, it looks like side angle side, but when you go to do the big triangle, I don't know that length. I'm trying to find it. So I won't have a ratio for that. So it can't be side, 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 can't be side, angle, side. It's got to be by angle, angle. So I'm going to say triangle RSV is similar to RTU by angle, angle similarity. I have to provide evidence. S is congruent to T, that's given, because it's been marked for us already. There is one other angle I can mark in here, and no, it's not vertical angles, and no, it's not linear pairs, because linear pairs aren't congruent. They add to 180. Angle R right there. R is a common angle. It's an angle in both the small triangle and the larger triangle. So angle R is congruent to angle R by reflexive property of congruency. So I have my statement. There's my similarity statement, the reason angle-angle similarity, and the evidence supporting angle-angle similarity. That right there explains why the triangles are similar. Now we need to solve for x. Well, x is part of the big triangle. So that whole length would be 10 plus x, and it matches up to the small triangle, length of 10. Now another proportion for another side on this is 12. 12 for TU and 12 for 8 for SV, so this equals 12 over 8. When I cross multiply, I'll have to distribute the 8 to this entire expression of x plus 10. That'll give me 8x plus 80 equals 10 times 20, 120. Subtracting 80 from both sides will give me 8x equals 40, and dividing by 8 will give me x equals 5. That's great, but in this case, unlike the last one, RT is not the value of x, because that's not how I chose to set up the problem. So if I answer 5, or if that was an answer on a multiple choice test, even though I've done all this great work, it would be marked incorrect. Because RT is the whole length. Segment addition postulate says 10 plus x. So 10 plus 5, which is 15. And again, they didn't tell us the units, so 15 units, whatever that is. Here's our last example, because we're going to look at example 4 in class. And then I'll ask you to try the you try problems. Letter C, I'm going to do on separate paper just because I want to be able to write out like crazy some of the numbers, but you should be able to fit it in there if you write small enough, or you're welcome to add an extra piece and staple it to your notes. They want us to find QR. So we're trying to find this whole, oh actually just this little piece of it. That's interesting. I can't do a proportion with pieces, not yet anyhow. We have to have some more information to be able to do that. So we've got to match up sides of similar triangles. We have a problem with this one, and that is that they did not give me 3 sides, because I don't know. I do know this piece. So I know this whole side and this whole side. I don't know this piece or that piece, and I don't know this side. So I can't do side, 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 and I can't even do side, angle, side. So we have a very big problem with this picture, and that is that I cannot prove the triangles are similar unless they give me something else. So I'm going to add that given for you now. Don't do this on a quiz or test. It would have to be given to you for you to do that. So here's the thing. The only thing left to use is angle-angle similarity. So I'm going to start by saying QSV is similar to RST, triangle RST, by angle-angle similarity. And I'm going to provide the evidence. I only need 2 things. Most of you already see one of the angles because it's a common or shared angle. So angle S is congruent to itself by the reflexive property of congruency. Now we can only use this and say it's congruent to itself because it is the exact same size angle for both the small triangle and the large triangle. Now the other angle that I can use, since I have parallel lines, if I trace those parallel lines, and you could do this on either the left or the right side, I'm choosing the right side, I see a letter with this angle and this angle. Now I could call this one angle V, but I can't call this one angle T because there's 2 angles at that linear pair there. But if you see the backwards F, those are corresponding with the parallel lines. So angle V is congruent to angle RTS. I have to use 3 letters to name that since there's 2 angles at vertex T, by corresponding angles postulate. So yes, those theorems and postulates were important, not just to be able to understand and prove, but we're going to be using them throughout the year, and this is one of the cases where we do use them. So I've got my evidence for my angle-angle similarity right there and there. We've said which triangles are similar and why. Again, you wouldn't have been able to do that without the given of parallel lines, and I just decided we're going to add that there. Otherwise, this triangle would be impossible to solve to show that it's similar. So anyhow, we're supposed to find x, which x is part of the whole side QS. QS. Now here's where I'm actually going to write down my ratios. I've got QS. QS matches up on the small triangle to RS. QS is 36. RS is whatever 36 is minus x, because it's this piece. Segment addition postulate says x plus this equals 36. So RS is going to be the whole thing minus the little piece x. The other side, notice I did big over small, so I got to do the same thing when I find another set of corresponding sides. The other set of corresponding sides is over on the right side of the picture. The larger one is 36. Oh, it's also 36. That's interesting. And that comes from SV. SV matches up on the small triangle to ST. The length of ST was given to us as 24. So here I have my proportion. I actually labeled the other 2 sides, like big over small, so I could see it. And when I cross multiply, 36 by 36 is 1296 minus 36 by x, so 36x. And 36 by 24 is 864. So I cross multiplied. Now I'm going to subtract 1296 from 864, giving me negative 36x equals negative 432. Lastly, I will divide by negative 36, which will give me positive 12 for the value of x. And then I go back to see what I was supposed to find, because that is the value of x. Well, we're supposed to find QR, which for this one was the value of x. So QS is 36, QR is 12. Had they asked us to solve for RS, then I'd do 36 minus 12, and I'd have the value of RS as well. This concludes the video notes portion for lesson 7.3. We'll work together in class on this last example, this application, and then you'll try some similar problems. Have a great day.